everyone. Welcome to Module 2 of the Risk Assessment course. This is GCU from the University of Minnesota, and I will be introducing the fundamentals of conducting risk assessments for chemical mixtures. This topic is crucial because in the real world, exposures rarely involve a single chemical. Workers and the general population are often exposed to multiple substances at once, making mixtures risk assessment both complex and essential. In this module, we will cover 5 key learning objectives. We will define what a chemical mixture is and describe different types of mixtures and outline the unique challenges that come with assessing risks from multiple chemicals. We will also compare different approaches to mixture risk assessment and look at examples in occupational and environmental settings. By the end of this module, you should be familiar with how to frame and approach mixture risk problems systematically. Let's look closer at the nanotechnology scenario we will be referencing. In this case, we're assessing a workplace where engineered nanomaterials are used in a spray coating process. A researcher sprays silver nanoparticle solutions onto fabrics to create antimicrobial surfaces. The process generates mist aerosol and results in inhalation exposure to airborne nanoparticles and dermal contact with settled droplets and contaminated surfaces. And in this slide, we want to identify specific risk assessment challenges in our nanotechnology scenario, which involves silver nanoparticles. Starting with hazard identification step, we know that silver nanoparticles may cause lung inflammation and immune effects, but the formulation also includes ethanol and some unknown surfactants. This introduces a mixture problem, multiple agents with different or uncertain toxicities. In dose response assessment, we run into a major barrier. There are no established occupational exposure limits, or RFDs, for silver nanoparticles. We also lack toxicological data for the surfactants used in the spray. This highlights the issue of no toxicological data being available. Next, for exposure assessment, workers are exposed via multiple routes. They may inhale the mist and also come into direct skin contact with spray residues. This is a clear example of a multi-route exposure problem. Finally, when we get to risk characterization, we hit a roadblock because of the missing toxicity values and complex exposure routes. We simply cannot calculate standard risk metrics like hazard quotients or cancer risk. So this scenario clearly demonstrates the real-world complexity of assessing risks from emerging technologies, especially when mixtures and data gaps are involved. Now, let's look at an additive manufacturing scenario focused on resin-based 3D printing. In this case, a worker is performing post-processing tasks on printed parts made with proprietary epoxy acrylate resin. The tasks include cleaning the parts with isopropyl alcohol or IPA, standing cured components, and storing them in poorly ventilated room. These work activities lead to multiple potential exposure routes. The worker could inhale volatile organic compounds or VOCs from the IPA and the resin, and could also have direct skin contact with uncured resin residues or IPA. This real-world scenario highlights the kinds of complex exposures that can arise in additive manufacturing environments and sets the stage for conducting a step-by-step risk assessment. Let's break down the risk assessment challenges for this additive manufacturing scenario. In the hazard identification step, we see that workers are exposed to a complex mixture that includes acrylates, epoxy monomers, and isopropyl alcohol. These substances may act as skin sensitizers, respiratory irritants, or even affect the central nervous systems. So, this presents a clear mixture problem. Moving to dose response, we hit a major barrier. There are no occupational limits and reference doses. Toxicological data is also limited or unavailable for key ingredients like photoinitiators or oligomers. This results in a lack of toxicological data. In the exposure assessment, workers may inhale VOCs released during the post-curing and sanding processes, and they may have experienced dermal contact with uncured resin and IPA. This means we are dealing with a multi-route exposure problem. Finally, in risk characterization, due to all these uncertainties, especially the lack of toxicological reference values, we are unable to calculate quantitative risk metrics for this scenario. And it highlights how challenging it can be to apply traditional risk assessment methods to emerging technologies. Now, I want to introduce the last scenario involving a novel drug delivery technology. Here, pharmaceutical compounding personnel are handling PEG lipid nanoparticles or LNPs that contain an investigational RNA-based drug in a DMSO solution. The tasks involve reconstituting the drug, transferring it to vials, and cleaning up any spills that occur during compounding. Because of the nature of the tasks and materials, workers may expose to both aerosols through inhalation and to the drug or solvent via skin contact during transfer and wiping activities. This example highlights the kind of occupational exposure challenges that can arise when working with emerging therapeutic technologies like RNA-based drugs via nanoparticles. Let's walk through the key risk assessment challenges in this novel drug delivery scenario. First, from a hazard identification perspective, the mixture includes a synthetic RNA drug, PEG lipids, and DMSO. These may trigger immune, reproductive, or systemic effects, but we lack a confirmed toxicological profile for the overall product. This makes it a mixture problem. Second, in the dose response step, we face a lack of toxicological data. There are no established occupational exposure limits, reference doses, or benchmark values for either the RNA drug or the PEG lipid carrier. In addition, we don't know how the components might interact. Third, in terms of exposure assessment, workers may be exposed through both inhalation and dermal routes, especially during compounding and cleaning. This represents a multi-route exposure problem. Lastly, when we try to characterize the risk, we find we can't calculate quantitative metrics due to all these data gaps. So formal risk characterization is not possible. We begin with hazard identification, where we determined what health effects might occur. But with emerging technologies, we often face mixture problems. For example, formulations may contain multiple novel ingredients or proprietary blends, making it hard to isolate individual hazards. In dose response assessment, the challenge is often the lack of toxicological data. Many of these new substances don't have established OELs, NOAELs, or benchmark doses, especially for nanoparticles, novel drugs, or custom resin blends. Then, in exposure assessment, we encounter multi-route exposure problems. Workers may be simultaneously exposed through inhalation and dermal contact, or even ingestion, especially in poorly controlled settings. All these limitations impact the next step, risk characterization, where we aim to combine hazard and exposure to quantify risk. But when data are lacking or exposure is complex, it becomes difficult to calculate reliable risk metrics, which ultimately complicates risk management. Here, we break down the two main approaches to mixture risk assessment, aggregated and cumulative. Aggregated risk assessment focuses on a single chemical and evaluates its risk across multiple exposure routes, like inhalation, dermal contact, and ingestion. This is important when one chemical is present in various forms or tasks and reaches the body through more than one pathway. Cumulative risk assessment, on the other hand, looks at the combined risks from multiple chemicals or stressors that have similar health effects or target the same organ system. For example, two different chemicals may both affect the respiratory system and need to be considered together. Together, these approaches help us understand combined and simultaneous exposures from multiple sources, which is especially relevant in modern occupational settings. This is critical for evaluating risks in workplaces where workers are exposed to mixtures of chemicals, emerging technologies, and non-traditional exposure routes, all of which complicate standard risk assessment approaches. And here we introduce several tools used to assess and manage risks in situations where mixture exposures and incomplete data make traditional methods challenging. Occupational exposure banding, or OEB, is especially useful when dealing with nanomaterials or novel pharmaceutical that lack full toxicological profiles. It provides a structured way to assign hazard bands based on available data, even when exposure limits are not established. Control banding offers simplified risk management guidance. It's helpful when precise exposure data or toxicological information is limited, allowing practitioners to take precautionary control actions. Stofan Nano is designed for working with poorly characterized nanomaterials in mixtures. It incorporates available data and conservative assumptions to estimate potential exposure and risk. Lastly, SDM 2.0, the structured deterministic data model, helps identify the controlling compound in a chemical mixture. It integrates exposure levels, volatility, and toxicity scores to prioritize risks and guide management strategies. These tools are especially valuable in emerging technologies where uncertainty and complexity are the norm. Here, we present three example scenarios. The nanotechnology scenario, which involves the use of silver nanoparticles in textile coatings. The additive manufacturing scenario, focused on resin 3D printing post-curing process. And the novel drug delivery scenario, which deals with handling PEG light nanoparticle therapeutics. All three scenarios introduce complex exposure situations involving multiple substances and exposure pathways. Traditional risk assessment methods often fall short in effectively capturing the risks posed by these mixtures. That is why mixture risk assessment is increasingly important. It helps us better understand and manage these complex, real-world exposures that workers face in rapidly evolving technological settings. There are challenges posed by complex exposure scenarios in emerging technology, specifically in nanotechnology, additive manufacturing, and novel drug delivery. However, mixture risk assessment offers a structured approach that accounts for cumulative exposures from multiple chemicals or stressors, addresses data gaps where toxicological information is missing or incomplete, and provides more comprehensive health protection for workers. By targeting key challenges such as the mixture problem, multi-route exposure, and lack of toxicological data, mixture risk assessment becomes an essential tool in model occupational health risk management.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies Program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.